Friends, I have so far delivered 25 lectures out of 40 lectures that I am supposed to deliver, which is about nearly 2/3 of the lectures. Essentially, during those 25 lectures, we have gone through some introductory sections, familiarity with ores and minerals, their processing, some general principles of extraction, general principles of refining, etc., etc. Then we had moved on to extraction of metals from oxide sources, and then extraction of metals from sulfide deposits. We are now coming to the subject of extraction of metals from halides. It does not mean these halides are naturally occurring in all cases. We will make a distinction between metals coming from naturally occurring halides and those that are not coming from naturally occurring halides, but from halides that are made from oxide sources. Why I have put them in this category is because many of these metals like uranium, although they are present as oxide, we cannot get it out of the oxide sources. We have to convert it to a halide, and from there we have to extract it. Whereas, in the case of metals like magnesium and sodium, you have halides in nature. In the case of magnesium, it is in sea water, sodium also is in sea water and elsewhere. From there we extract the metal. So, there is a distinction, but in both cases we are getting the metal from starting point, which is some kind of a halide. Now, by now you should have realized that even though some metals may come from the same kind of ores, the process to be followed are not the same always. There are peculiar differences in the properties of the metals or the nature of ores that necessitate it to go for appropriate extraction steps, and they are different for each metal. Say we talked about magnesium. We got magnesium from dolomite or calcite, carbonate of magnesium or magnesium carbonate. It could decompose, produce the oxide, and then go for carbon reduction. This obviously seems more rational approach. The oxide reduced by carbon. That was done for tin oxides also, which come for tin ores. Very largely also for ferroalloys. Ferroalloying the ores which are ferroalloying elements, basically oxides, we could reduce them by carbon. But we had other processes too. For example, ferroalloys can be produced by aluminothermic reduction. Sometimes that is advantageous, there will be no carbon in them. But take the case of aluminum, easily available as aluminum oxide, hydrated bauxite, but then we cannot reduce it by carbon, because the carbide is very stable, and we have to now produce pure alumina, dissolve it in a fused salt, cryolite, electrolyze. So, we have to go for a very different process. Similarly, consider sulfides. They are the main metals for copper, lead, zinc. Copper is unique in the sense that we did not have to reduce anything. We had copper sulfide and iron sulfide. If they were oxidized in a controlled manner, iron sulfide oxidized first, it was slagged out, we were left with copper sulfide and some iron sulfide. Then further oxidation and removal of iron sulfide, we were left mostly with copper sulfide, and once it formed Cu2O, then there was a reaction between copper sulphide and Cu2O and copper came out. So, there was no reduction step anywhere. What we did is actually just removed the sulfur out of the system and other things out of the system, you had copper there. That does not work for lead sulphide. Now, lead sulphide had to be roasted to make lead oxide, then we reduced it in a blast furnace, no problem there. In the case of zinc sulphide also, the zinc sulphide was converted to an oxide, then pyrometallurgically it can be reduced by carbon or dissolve zinc oxide in acid solution, and then that solution is electrolyzed after of course, a lot of purification, because if you do not have a absolutely purified liquor, then zinc cannot be electrolyzed from aqueous solutions. We have discussed the details of these. Now, very interestingly, copper sulphide, lead sulphide, zinc sulphide, very often they are mixed together, they are found at one place, but you cannot apply the same method for all of them. Fortunately, there is now a process called imperial smelting process, where in one blast furnace we extract at least 2 metals. You know that we get zinc distilled out of the blast furnace, and then there is a method of quenching it in lead and separating lead and zinc, and lead comes out from the bottom as a normal blast furnace operation. It is claimed that if there is copper, that also comes out as a separate matte phase, but the imperial smelting process does not work so well when there is copper as well. So, it is ideally only for lead, which comes out at the bottom of the blast furnace, and zinc, which comes out of the top as vapors. Now, we are now through with metals from oxides and sulphides. We are going to talk about extraction of metals from halides. And to start with, we will start with extraction of reactor metals. What these are, I would explain. What are the learning objectives here? First of all, I would like to say a few things about the importance of halide metallurgy, maybe not right at the beginning, but during my lectures. I make the distinction once again between naturally occurring halides as a starting point, as it is for magnesium and sodium, and halides produced from oxidic ores. We will see many examples of that. Then extraction of nuclear reactor metals. I would like to discuss separately. These are uranium, plutonium, thorium, zirconium and beryllium. These are called nuclear metals, reactor metals, because they all have important roles in nuclear reactors. You all know that the nuclear reactors will not be nuclear reactors without uranium. Uranium is the most important element, and right now the only element from which we can think of producing nuclear energy. Plutonium is a man-made material, which comes from, we will see how from where it comes from an isotope on uranium. Thorium itself is not one that undergoes nuclear fission, but thorium can be converted to a fissile material, and we will discuss that. So, uranium, plutonium, thorium are the elements which will be required in nuclear energy production. Zirconium has a different role. It comes in the construction of tubes in which the nuclear metals that will undergo fission will be contained. After all, we need a place to keep the materials undergoing fission. And there we will need zirconium based alloys, because zirconium has an advantage. It does not absorb thermal neutrons, because if thermal neutrons get absorbed, then they would not be able to carry on the fission reaction. Beryllium has an opposite role. It is a moderator. It can slow down thermal neutrons. So, we will need both this and this in the construction of nuclear reactors. Now, all these are also known as reactive metals, because they are very reactive, they produce very stable oxides, and because they produce very stable oxides, in theory they can be reduced at high temperatures by carbon, but they will all form carbides. So, carbon reduction is not something that we can think of when they are in the oxide form. That is why we have to take them into the halide form and see how we can reduce the halide suitably to get the metal. Apart from these reactive metals, there are also other reactive metals like magnesium, alkali, alkaline earth metals and titanium. These are also high up in EMF series, they form very stable oxides, they cannot be also easily reduced by carbon. For them again we have to think of some other route, and again it is usually the halides will fall upon. Now, there is special importance of nuclear reactor metals today in Indian context, because we want to expand our nuclear energy production drastically. Titanium, because we have big deposits of ilmenite and we are producing TiO2, which goes for paint industry, but we are not producing titanium, whereas titanium is a very valuable metal which goes for aerospace alloys, all kinds of light metals where titanium and aluminum alloys are a must. So, we will touch basically all these. The books I have referred to earlier will have many details. I will not go into too much of detail, but I would certainly show you some flow sheets, and I will again say when you see a flow sheet, do not get scared of these blocks and arrows. Flow sheets just tell us what are the essential steps, and you are not supposed to remember everything, but you must understand how those steps come one after the other. Basically, I have to show them to give you the logic or rationale of the processing of ores and minerals for production of those metals. Please remember a very important saying of Einstein, and I saw it near the airport in Kolkata. As you come out of that, there is a big hoarding in which it is written, and it said that I do not need to know everything. I just need to know where to find it when I need it. So, in much of your studies, you should know what is where, and once you know that, when you need to study, you go there. So, these lectures that I am delivering, some references that I am showing you, just gives you the idea that in case you need to know more details, where you should go to, and you pick up the details. But then it helps if you know the logic, if you follow the steps, why they come one after the other, what are the tricks of the trade in each step. And once you get familiar with the subject, you will get to know that many things that the metallurgists do have come from many years of experience, knowledge of fundamental chemistry, and in principle they are actually quite simple, and certain things are repeated again and again in different extraction processes, and that knowledge will come to you as you study the subject. And stop getting scared of the flow sheets. Flow sheets are nothing but repetition of certain what we call steps that are carried out in different extraction processes. Okay, with that, let me proceed now. We are to talk about nuclear reactor metals. Now, in the case of all these metals, the ores are actually very low grade and complex. If you talk about a uranium ore, you cannot find an uranium ore like iron ore or aluminum ore, where the aluminum or iron percentage is very high. It is not so. You will see later on an uranium ore means an ore where uranium content may be less than 1% or even smaller. So, we are essentially would be dealing with low grade and complex ores, which will require equally complex mineral beneficiation processes, some of which I have touched in the initial stages of during my lectures. There would be initially a physical or chemical method of beneficiation and will produce a concentrate. This is now true of many metals and their ores, and it is becoming even more important as time goes by, because ores and minerals are becoming gradually low grade. Now, there was a time when those who were in the business of producing metals could go to a mine and hand pick certain parts of the mines which apparently were richer in the metal content. But that is no longer allowed today, because if you were to pick and choose the particles which are richer in metal content, then you are leaving behind a deposit which is now poorer in grade. So, your extraction process for the future generations will become more difficult. So, the general government policy is that you take what you get, you do not select from the mines this particle or that particle or that particle, the looks of which tell you they are richer in that particular metallic value. That is not allowed. So, you have to mine the whole thing and develop your process that will be suitable for dealing with low concentration of the metallic value. Now, once you got a process like that standardized, then it will apply for the rest of the ore body also, which is also poor grade. So, you are not doing anything special for a selected batch or selected sample. So, essentially we need physical and chemical methods of beneficiation, some of which I have discussed earlier. There are many physical methods. In the case of sulfide deposits, we found we can do flotation, and in one step an ore body which at 1% will produce a concentrate of 25% or 30% copper. Same with zinc or lead. In the case of oxides that we dealt initially, we did not have to worry about concentration so much, because ores were very concentrated. But when we come to reactor metals, we will find we will need greater application of mineral beneficiation techniques. We have to think of magnetic separation, because many minerals are magnetic of different susceptibilities. Some can be removed by weak magnetic force, some would require stronger magnetic force, some even stronger. There can be methods based on size, density, shape. We discussed once a method which we called a spiral, that using a spiral from beach sands we can separate different fractions depending on density, shape as well as particle size. That kind of thing would be required here. Incidentally, there are many more methods where minerals are separated based on density, shape and size using essentially the same principle, that the way they would settle would differ from one mineral to other. So, in this case of spiral, certain properties were used. We can have tabling, you may have seen tabling. We have cyclones, hydrocyclones. There are other methods. There can be electrostatic separators, where the news of the electrical charges are giving, and based on the charges acquired they can be separated. So, magnetic separation, electrostatic separation, the separation based on density, particle size, and there are other methods also. If you go to the books, you will get all the details how they are done. I will not go into the details of these. Then there are chemical methods of separating one mineral from the other, which are sometimes much more selective. Like if you have a complex ore body with many minerals, we can chlorinate, take out a volatile chloride of one particular metal only, then change conditions, get another metal as a volatile chloride or a liquid chloride, and then the third metal. More frequently, we try to beneficiate by selective leaching, that we leach out one metallic value, leaving the others unleached in the residue, and from there again there will be further leaching processes for getting others, and once we leach, from that we can precipitate, or we can go through solvent extraction, ion exchange for purification. The idea will be to produce a pure compound, and once we have produced a pure compound, we will move forward. So, we can have chlorination, fluorination, leaching, which can be acid leaching or alkali leaching. These will be chemical methods. Then once we produce a concentrate, our goal will be to treat the concentrate to produce a pure intermediate. Now, recall that when we talked about purification of metals, I had said basically we follow two approaches when it comes to refining. In the case of pyrometallurgy, the goal was to produce a whole lot of metal as much as we can, as quickly as we can, irrespective of what all impurities come in. So, the idea was to produce the impure metal in bulk, then go for purification, like we did in the case of lead, an elaborate purification, in the case of zinc, in the case of copper. The other method will be to produce first a very pure compound, which means we do not want to produce whole lot of that metallic value with impurities. We start with enough care to produce a pure intermediate, and once you have got a pure intermediate, from there what you produce the metal will be very pure. This will be the essential approach in the case of nuclear metals, reactor metals, as well as other metals that we are getting from halides. So, once we have recovered pure intermediates, and we will also recover valuable byproducts from which we will get other things, this pure intermediate is reduced to produce metal, and that metal will be pure. Of course, very often even if we take a pure metal, pure intermediate, we may be able to produce a metal which may be pure, but it may not be physically in a form that is acceptable. Like suppose we have a method and we reduce and we end up with very pure fine powder. Now, these are very reactive metals, mind you. So, if there is a fine powder, there is always the danger of them getting reoxidized. Even if you keep it under inert atmosphere or under vacuum, even the slightest partial pressure of oxygen will produce oxides, at least on the surfaces of the powder. So, once you have got a powder, we cannot leave it as such. We will have to go for a final refining and consolidation of the metal. We have discussed some methods for that. It could be vacuum arc melting. Essentially, if we remelt it under vacuum, ensure that all gases are removed, and once we make a consolidated metal in bulk form, its surface area would be low. So, the chances of reoxidation would be low. So, please remember, these are the standard steps we will need in the case of most of them. Start with a low grade complex ore, go through physical or chemical methods of producing a concentrate. Then from the concentrate, we produce a almost pure intermediate. From pure intermediate, we produce a pure metal. Then although it is pure metal, it may not be in the correct physical form, or it may have some gaseous impurities. So, we go for refining and consolidation. This is what we will do. Let me start with uranium. Now, before I start with uranium, I would like to impress upon you the enormous importance of uranium today. Uranium we need because we need nuclear energy. Nuclear energy is a highly debatable subject. Unfortunately, we also have many wrong notions about nuclear metallurgy. I do not know how many of you know, there is, especially in some states of India, where there is an inbuilt bias against the nuclear metallurgy. West Bengal is one of them. There were proposals to have nuclear reactors in Sundarban area. Now, there is a proposal to have somewhere near in Purulia area. They have all been very strongly opposed by many people, political parties as well as many intellectuals. Their fears are not all wrong. After all, we have had Chernobyl in Russia, and that created a tremendous fear about nuclear reactors. There have been some accidents in one or two other places also. But then many people have argued that look at France. France does not have its coal. They cannot have thermal power plants unless they import coal. They do not have oil fields. So, they cannot have thermal power plants based on imported oil. They do not have natural gas. The England is very lucky. They have the North Sea oil fields which produce gas also. France does not have it. So, what did France do? The French have gone in a big way for nuclear energy. 80% of their demand, country's demand, is met by nuclear energy alone, and they are the leaders. There has been no accident in France so far. It does not mean it may not happen, it has not happened. The other objection, so about safety, I can also say, if you go for any other source of power, nobody guarantees you safety. If suppose you go for hydroelectric projects, you have heard about the dams collapsing because of earthquake, or collapsing because with age the strength has gone down and dams have burst. And remember, do you know what it means when the dam bursts? You talk about thermal power plants. Thermal power plants today is a serious threat in terms of climate change. It is causing slow poisoning, and the amount of CO2 the thermal power plants are throwing out in the air is causing millions of deaths. It may not be an immediate death, but it is it's a matter of concern. So, people are thinking of taking CO2 and putting it somewhere in the ground, store it in the ground, and there are processes which are operating pilot plant. This brings me to the other fear about nuclear power, that after undergoing fission, what do you do with the nuclear waste? You know, it is a very complicated subject. The waste is radioactive. So, first of all, it has to be taken into some kind of a glass. The glass, because the glass does not easily get leached, then it has to be put in steel containers, maybe 1, 2, 3, and they have to be put under rocks or in the sea. Now, the experts who know, they say they have now done enough work for safe disposal of nuclear waste. So, the question of disposal of nuclear waste has been addressed. Nuclear reactor accidents should also not happen if you know how to maintain. And nuclear reactors are now going to expand everywhere, even in those countries where there is enough oil, enough coal. Think of Iran today. Iran is not going for nuclear reactors only for making bombs, at least they are claiming they also need nuclear power. China, they have a lot of coal, but they are also going in a big way for nuclear reactors, and they are proposing an big expansion in a number of nuclear reactors. I will come to this subject towards the end of this course when I discuss environmental problems. India started off very early, but we have kind of fallen behind. As of now, we are producing just about 3 to 4% of energy, 3 to 4% of our total energy demand, but there are plans to take it up to 20 or so in foreseeable future. And by and large, planners are approving of this thing. Now, the problem is, without uranium we cannot get started. I will tell you why I am using the word get started. Something will come later, but we need uranium to start with. We do not have enough uranium in the country. And that was the basis of all these things we had between America and many other countries, all the proliferation treaties, and many countries have almost accepted India into the club, and there are countries coming forward to give us uranium. I read recently Australia, which has large reserves of uranium, are also now beginning to see merit in supplying uranium to India. India does not have much uranium. There are some small deposits, and I will come to that later on, and there is search is on as to where we can find uranium. So, now leaving it there, let me come to the subject as to why uranium is so important. But before that, let me quickly go through, if we had uranium, what we will do. What we will do is what we will do in the case of many other reactor metals. We will produce a concentrate and then we would leach it, and after leaching we will try to produce a pure compound. In the case of uranium, for example, U3O8 is the oxide you are aiming at. It can be leached by sulfuric acid taken into solution as a sulphate. Incidentally, this is also amenable to bioleaching. Remember I had mentioned one, there are all kinds of bacteria which can speed up natural process of sulfuric acid leaching of oxide deposits. This work is also going on in our country, where there are low grade uranium ores. We can identify some bacteria, and those bacteria, if left there, they will leach automatically. It will be very much suitable for low grade ores, because it will produce a leach liquor. We would not have to go through elaborate processing, but that is a long run process. Now, same thing kind of would be applied for when you come to thorium. We will say if you produce thorium concentrate, that can also be leached by sulfuric acid taken into solution. If you start with a beryllium ore, which is written like this can also be leached by sulfuric acid to take beryllium in the solution. Now, these are three examples of acid leaching. There are also alkali leaching processes for all these, like thorium can be leached by sodium hydroxide, zirconium, sodium hydroxide, uranium can also leached by an alkali to produce uranium in solution. Now, there is no agreement as to what will be best, will it be acid leaching or alkali leaching. There are many countries which go for acid leaching. I will see later on that in India, so far as uranium is concerned, and many others, we go for alkali leaching. Now, here is a general principle. Acids are usually much stronger leaching agents. By stronger, I mean they will act quickly, they will leach more in a shorter time, but they would leach a whole lot of other things also. Not only uranium, they will take into solution some of the other metallic values you do not want, even you try to control the conditions. Whereas, in the case of alkali leaching, the leaching is a milder process. It can be more selective. So, you can have a selection step during leaching itself, provided you settle for longer duration or lesser recovery in a given time. Now, some people will opt for this, some people will opt for a stronger leaching and worry about the impurities subsequently. It depends on who likes to do what. We will give examples of both. So, essentially from leach liquors, we will try to produce a pure oxide. This is the whole game. So, the thing, take a concentrate, leach by acid or by alkali, take the metallic values in solution, the rejects go for recovery of byproducts, which are also valuable, and finally try to produce pure oxides from the leach liquor. From that oxide again, we will have to convert it into some halide, chloride or fluoride, because from oxides you cannot go to the metallic state. We will have to go to the halide or fluoride, and then we will proceed further. Okay? Now, one very general method that is applied in many cases is to take an oxide and convert into a chloride, which could be a liquid or it could be a gas. If it is a volatile chloride, then the gas will be taken out and condensed. If it is a liquid, of course, the liquid will be drenched out. Now, if there are many metallic values, one can control the chlorination temperature and or partial pressure of chlorine to recover one metallic value at a time. Means you take out metal 1 as a chloride first, then you change condition, take out another metal as another chloride, either vapor or liquid, and 3, 4 can be taken out from a mixture of several chlorides. Now, if you recall, I had discussed the thermodynamics of chlorination and pointed out that there are two kinds of chlorination. When we chlorinate, just take an MO2 and react with Cl2, you produce a chloride, it is called direct chlorination. This happens in the case of oxides, some oxides which can directly form a chloride, but some do not do that. You have to bring in a reducing agent, carbon, and this we call chlorination in presence of carbon. There are thermodynamic reasons why we need carbon. Essentially, it is for those where the oxide is very stable. The carbon kind of reduces to metal, metal reacts with chlorine and produces the chloride. If sufficient carbon is present, then CO by CO2 ratio governed by temperature. So, the temperature is the crucial parameter. And as I have said, relatively less stable oxides can be chlorinated without use of carbon, but many oxides cannot be directly reduced chlorinated by chlorine unless there is carbon in the system. Now, we can do similar things with chlorine or fluorine to break down complex minerals to produce halides of different metals at different temperatures. This is done from the whole bunch of things, and very often these ores are very complex. We can separate. So, this is an example of chemical beneficiation. Now, once we have produced a halide this way, then there is a very logical thing to go for metallothermic reduction of halides. By metallothermic reduction means you bring in a reducing metal which will form more stable halide. Very often it can be calcium or magnesium. Why want to go for metallothermic reduction of halide? Because then we are not using any oxygen in the environment. We will get a superior metallic product which will not react with any oxygen in the environment. And the choice of reduction method will depend on many parameters. So, it will depend on thermodynamic feasibility and kinetics obviously. At what temperature you will do, it will depend on that, and it will depend on the reducing agent you are using, calcium or whatever. It will depend on heat balance. We would like to go for those reactions which produce lot of exothermic heat. The reaction will become easier. We will be able to melt either the metal or the slag or one or both. Melting boiling points of the constituents are very important. Supposing we see that we need a temperature in which the reducing agent that we want to use needs to be a gas, then you have to have a bomb, you have to have a reactor which is closed and which has to be under high pressure. This is too complicated. We do not want that. We want a process which will take place at a temperature where the reducing agent will not have to be under pressure as a gas. If it is there as a solid or a liquid, fair enough. Then we also have to worry, what about the product? If the product comes out as a gas, then again we have a problem, that how do you collect it? So, what will happen to the at the required temperature to the physical states of reaction products becomes also a criterion for choosing the metallothermic process. And of course, the densities of metal and slag are important, because we need a metal slag separation. So, you see, you simply cannot go like we can do that in chemistry, that this reaction will take place, this reduces that, this will be produced. No, we are talking about practical considerations. It may be okay in theory, will it be okay in practice? Will practice allow this process? This becomes a very important criterion in metallurgy, because we are talking about actually handling a raw material, producing a concentrate, producing a compound, then actually producing a metal. So, we need to have conditions which suit practical operations. I will try to touch on these here and there. Now, let me start with uranium and let me re-emphasize the importance of uranium. You are not going to be a nuclear metallurgist unless you join BARC, but in today as a metallurgist you must know some fundamental principles so far as production of nuclear metals are considered, why they are important, what are the issues that are important. You must know, otherwise I do not think you can be called a metallurgist. Now, in nature uranium has 3 isotopes. One is uranium-238, which is the bulk of the substance, 99.28%. Then you have uranium-235, which is only 0.7%. Means it is less than 1%. This isotope is fissionable. Fissionable means if it is bombarded by thermal neutrons, then if it absorbs 1 neutron, it will absorb more than 1 neutron. So, that that neutron again bombarding it will produce more neutrons. This is the basis of nuclear metallurgy, that you gradually increase the neutrons as through fission reactions. There is another isotope U-234, 0.005%, it is not important, we are not interested. But now, it might seem to you that uranium-235 is not that important, 0.7%, though it is fissionable, and you might think that, well, if this is not fissionable, what is the use of 99.28%? Try to understand now some very interesting things. Uranium-235, which is 0.7%, is definitely very important, but there is another isotope which is uranium-233, which can be produced by neutron radiation of thorium-232. This is actually the most important isotope of uranium that man can produce artificially from thorium-232. So, thorium becomes very important and India has thorium deposits. But to come to that stage, we have to start first with uranium, normal uranium and uranium-235, and we will come to this later. There is another interesting thing is, you might think uranium 99.28%, which is not fissionable, is not important. That is not true. This isotope is a fertile material. Fertile material means it can be converted to plutonium-239, which is fissionable. So, uranium, see the beauty, uranium 99.28%, which is not fissionable, can be converted to plutonium-239, which is fissionable. So, it is called fertile material. By itself is not fissionable, but it gives rise to fissionable material. Why it is fertile? Again let me repeat, it is fertile material because neutron irradiation converts it to plutonium-239, which is fissionable and source of far greater energy than obtainable from fission of uranium-235. It should be obvious, uranium-235 is only 0.7%, but we have uranium-238, which is 99.2%. So, what we can convert it to plutonium, we will have a lot more fissionable material. Unfortunately, there is a problem. Uranium-238, when converted to plutonium-239, does not all become plutonium-239. Only very tiny fractions of uranium-238 after irradiation produces plutonium-239, and there is a great deal of problem in recovering that plutonium-239. Very elaborate chemical engineering processes. Anyway, let us go through all this once again. You have uranium. One has to find a method of separating the isotopes. How we will do it, I will very briefly discuss later. We will have to separate uranium-235, and uranium-235 is the one which can undergo fission. Which is fission? Then when bombarded by thermal neutrons, it will break into two products, fission products of equal mass, which will go at very high velocity in different directions, and it will produce neutrons. It will produce more neutrons than it has consumed, and those neutrons would again bombard U-35 and produce more neutrons, and so the energy goes multiplying. So, after fission there is energy in the products which have gone fly in the opposite directions. Then there are thermal neutrons. These neutrons can be used to bombard U-238. This U-238 will get converted to plutonium-239, which you have to separate it out, and then that will produce energy. So, in the first generation we will have a reactor working on uranium-235, then we will go to next generation, where those thermal neutrons would be used to produce plutonium. Actually, in any reactor, whenever a fission reaction is taking place, plutonium is always being produced, and that is the plutonium extraction becomes a very critical process. Similarly, the thermal neutrons can convert thorium-232 to uranium-233, which is a fissionable material. This is an isotope which comes out of thorium-232 by reaction with thermal neutrons. These are the fission reactions. Uranium-235 bombarded with neutron produces fission products, more neutrons and energy. Atomic products are rejected in opposite direction in extremely high velocities, carrying enormous energies. We have to find a way of extracting those energies. In the case of uranium-238, which is a fertile material, neutron U plus uranium-235 plus neutron will give uranium-239, which has a half life of 23.5 minutes. Then NP-239, half life of 2.33 days. Finally, it converts to plutonium-239, which is stable. Half life is 24360 year. So, uranium-238 has now been converted to a man-made element which is stable. Neptunium and plutonium are transuranic elements. 1 gram of uranium can release nearly 4 into 10 to the power 7 times energy as from 1 molecule of TNT. So, you see how much of energy there is 1 gram of uranium. Now, coming to thorium-232, reaction is plus N, thorium-233 half life 23 minutes, and palladium 27.4 days, finally, uranium-233, which is stable. This will be a fissional. Now, finally, number of neutrons emitted by a fissile nucleus per neutron absorbed is called eta value. We find uranium-233 gives 2.30 number of neutrons per neutron absorbed, U-235 2.06, plutonium-239 2.03. Therefore, the uranium-233 which comes from thorium fuel cycle is most highly promising. Okay, I stop here now. I continue with it in the next lecture. Thank you.